Anyway, so wave basics. All right. So what are we going to do in here? We're going to look at explain a wave as the transmission of energy through a medium without the net transfer of matter. That, oh look, yeah, and it's going to be on YouTube. Your lateness is going to be on YouTube. So I'm filming this. It's can't. All right. So, all right. So this is an important one right here. Explain the transmission of energy through a medium without the net transfer of matter. So when we're talking about waves in this context, it's about energy moving through a medium. Now, remember, we did a lot of talking about how a medium was very, very important when it came to this transmission of sound. But, what form of energy doesn't need the medium? Yeah, light. So remember all of that nonsense about the ether being invented because light needed a medium, and then they did a whole bunch of experiments. What was the experiment? It was Michelson and Morley. Yeah, Michelson and Morley. That's right. That's right. So Michelson and Morley try to prove the ether's there, and then just do the opposite and prove it's not.
I've got a question about this. So they had one way going with the ether.
Yeah.
How did they decide which way the ether?
I think it didn't matter. Basically, it's because the ether is not moving, and the planet is moving through it.
Yeah.
So they're like, okay, so at some point it's going to be moving in one direction. Yeah. So, and that was them trying to come up with the idea that there was an absolute reference point, and then eventually they just had to let it go and say, no, there is no absolute reference point. And then when they understood with Maxwell's equations, they figured out, it actually just it's self-propagating. The light does it itself. It doesn't need anything to travel on. Yes?
Is that Michelson-Morley thing on the exam?
Yeah, it can be. It can be referenced. It can be referenced in there. But one of the examples is what was Michelson and Morley, what were they trying to prove, right? And then they'll give you like a multiple choice selection. And of course, they all sound great. But if you really dig down and go, what were they actually trying to do? They were trying to show the existence of the ether. Right, that was technically what they were doing. Now, double check that in case I've forgotten and picked a different answer, but just double check that. But I believe, if I remember correctly, that's what they were actually trying to do. A really important thing here is that this chapter on waves is really about waves that move through a medium. So things like sound waves, okay? That's the major one that we look at here. So if you look at this beautiful model here, which I'm going to bring into shot, okay, so someone created this crank, right, and all of these bars are separate. See, they all are independent of each other, okay? Now, when you turn this crank, it gives you the idea, it kind of demonstrates this first one here, where the transmission through a medium without a net transfer of matter. That's the key. This is one of the concepts, one of the ideas. See, if you imagine like wave on a water, and as though every part of the wave is broken up into little bits, then each bit moves independently of every other bit. It only responds to the energy that's going through, right? So when you turn this crank, you can see that like there's a crest moving along. Okay, there's this crest moving along. But it's made up of all of these individual pieces. So you can see the wave is moving, but the particles are only just going up and down. Then the particles themselves aren't moving left or right. They are simply moving perpendicular to the transfer of the energy. So this is the classic example of a transverse wave, okay? A wave that looks like the wave you would expect, all right? There's the transverse wave. So there is a transfer of energy with no net transfer of matter. So when the wave has gone past, the particle should end up roughly where it was before. That's the idea, okay? So the particle doesn't go left or right. And there's a bunch of questions in practice that test your understanding of that idea, all right? Okay, so that's the first idea. Now, there is a different kind of wave. There's the transverse wave, and there's also the longitudinal wave, This is the transverse wave. Goes up. Now, so the transfer of energy is perpendicular to the motion of the matter. The matter's going up and down, but the wave's going left to right or right to left. So the matter doesn't move left or right. And that's what this model is there to really, really show. The matter itself never moves left or right, even though the wave you can see is moving along. All right? And that's the key. That's what the point of that is. All right? Then there's a longitudinal wave. Look how clever they are, science people. Look at this. Got to love the science people. All right. So here you can see, and I'll show this in a couple of different orientations so everyone can see it. A longitudinal wave, can anyone guess one typical version of a longitudinal wave? A wave that is like compressions rather than like a wave, like a... Well, the energy moves in the same direction as the particles. Ooh, a spring, yeah. When you let a spring go, yeah, you send a wave through it like a slinky. You can see the particles are moving left and right as the wave moves through. So it's moving in the same direction as the motion of the energy. Now, these are the particles. As I crank, there's a compression that occurs. And you can see the compression is moving down. See that? So the particle, each one of these particles, for example, as you can see, only has a certain limited range of motion. Moves up and down a little bit. But as they do that, they're passing the energy on to the next particle and then the next particle. So you end up with this compression that moves down. And so, of course, each little bar individually just ends up where it was before, but the compression is moving through. Now, that's me explaining the idea that the energy is moving in the same direction as the particles themselves.
So that energy be going down.
Yeah, that energy is going down, but the particles themselves are going down, up and down as well, in the same sort of plane as the motion of the energy. Whereas in transverse waves, the particles are going perpendicular to the motion of the wave.
If you drew that one, instead of looking like that, it'd look like a Wi-Fi bar.
Yeah, like that. Yes, like the Wi-Fi symbol there. Yeah, it's doing that. Yes, and propagating that way. Yeah.
So what? When they all get really small, that's compression. But then when it gets larger,
So that's what we do here. Let me get this out of the way so it's not in people's way. Okay, so what we've got here is when we go through all of this stuff, we've got a longitudinal wave drawn, and as you can see, it's like through a slinky that represents how air moves. And then you've got a transverse wave where the particles are moving up and down. Now, when you actually look at how they line them up, because they're kind of examples of each other, and they both have things that are similar. Okay, as in that you can read. So, for example, here the movement of particle is in this direction. This is a longitudinal wave. And here the movement of the particle is up and down, as we said. Now over here, you have a compression, okay? So this is a position that lines up with the peak of a transverse wave, okay? So this is a compression. And then in between, you have roughly if this was air pressure, you basically have roughly the same density of matter of the medium. You have the same density as normal, because it's kind of in between high pressure and low pressure, okay? And then you've got the next bit here, which we call, now this is the region of the least amount of pressure where you saw where the particles stretch right out before they start to come back again. This is called a rarefaction. Here, a rarefaction. It's a weird, ugly word. Okay, so this here is a compression, and here is a rarefaction, and that's high pressure and low pressure. Okay, so that is basically half a wavelength in between. You can see that's half a wavelength in between. How do you measure the wavelength? There are only a couple of measures that you can have for these waves. One of them is the wavelength. Wavelength is peak to peak. All right, so you should know that already, I hope. Peak to peak is the wavelength. So that's one measure. And of course, we do this in meters. And of course, they're going to give you examples of questions where they give you in centimeters and millimeters. Just be careful that you are aware of your units. Okay. There's another measure. Now, this is an important one as well. Every medium has a certain speed. Okay. So there's the speed of the wave through the medium. Okay. Now, when it comes to speed of light, it's kind of not the same thing. It's different because the speed of light is c. Okay. It's always c, and it kind of does line up basically to how these work as well. Because if you think about it, we have something called the wave equation. Can you see this? Yes. The wave equation v equals f lambda. Okay, so that v is the velocity. Actually, I'll make it a nice small v just to keep it with the way I normally do velocity. V equals f lambda. So the measurements that you have here are the frequency of the wave. You've got the frequency of the wave, the wavelength, and the speed of the wave. Now, the speed of the wave, if you're talking about water, a wave moving through water, it doesn't matter if you're hitting the water. Like, for example, you're using a little ball, hitting the water, making waves, making ripples, right? So if you make those ripples go if you agitate the water rapidly, so high frequency or low frequency, each wavefront, because you're in water, okay, is moving at the same speed. It's not like the speed of the wave is fixed by the medium, all right? The only difference is when it comes to water, is if you have water that is, like, for example, out in the deep ocean and it's coming into the shallows, all right? That's the only thing that's different. So when you put a wave on this water, it'll have a certain speed, okay? But as it comes into the shallows, it'll slow down, all right? It'll slow down, and this is why tsunamis become, like, devastating, because the waves at the front are slowing down, the waves at the back are catching up and they build on each other and then become really devastating. Okay, whereas out in the ocean, as a tsunami goes past you, you would probably not notice it because it's just moving through a very, very thick column of water. So yeah, it'll just be a little nothing. But then at the beach, it's massive. All right, because that's the only thing that will change the speed. So often in questions, they'll be like, oh, okay, in a constant depth pool, you know, they have to say that because then you can say, oh, okay, the speed won't change. V will be no part. All right. Oh yeah, I neglected this one. Amplitude. The amplitude is just like the amplitude that you use in maths. It is not peak to peak. It is from the middle. The amplitude is another measure. Okay, another measure, and the wave velocity is obviously in that direction.
What is amplitude on?
Well, actually, you use amplitude very little in this because most of this work is really about the speed of the wave, wavelengths, the period, all those sorts of things. They're what we talk about a lot and what we do calculations on.
Waves are sine wave pretty much.
Yeah, you can, and that's what you'll often find in questions. What they've done is they have said they'll give you a model of a sound wave, a question about sound waves, but they will give you a diagram of a transverse wave because it's just easier to visualize and easier to work with. And so they say, okay, so that's the compression. There's the rarefaction. All right.
So rarefaction just means when it's furthest.
The furthest apart. Yeah, that's it. It is. All right. Superposition. Yes, superposition. That's fun. But for now, just to see if you can see superposition, two waves that interact with each other will interact with each other just like, have you done in maths addition of ordinates?
Yeah.
Where you draw two graphs, one graph on top of another, and you add the y values to them. You add each y value of the two graphs, and you can draw a new graph.
Oh,
yeah. I remember Mr. Seymour teaching me that back in like the 80s. So yeah, that's. And so he was my teacher for like
Was that in high school?
in high school. So addition of ordinates is just something that comes from this like, well, this idea lends itself beautifully to it. So basically the y values of the waves, they add up to each other. So if you send one wave up against another one, when they interact with each other, if they're both above, then they add to each other at the same amount, conservation of energy that they both have. So, or if one hits above and one hits below, then they subtract from each other, just like they do when you do the graphs. Okay. Yeah, they cancel each other out. For that instant where they are, the energy's still there because after they cancel out, they keep going, right? So I can try to send two pulses. Like if I send one pulse, it hits the back and then it just keeps traveling, right?
Whoa.
Right? But if I try and send two pulses, you might be able to see something if you kind of quicken up. Okay, let's try. They kind of like freak out when they hit each other. All right, and that's because that's too close. I've got to wait for one to come back before the other one. All right, so if I go one pulse. Oh yeah, I think I did it just then. I was waiting for the first one to hit and then to come back, and then you see them go all funky in the middle when they meet each other. Like try to see that. So there's one, and then send another one.
Whoa.
All right. So yeah. So the important thing though there is you may have seen a bit of a flat spot. Is when you see it, right? See if you see that flat spot that happens. Well, there's one, and then there. Okay. You didn't see it in the first one. All right. So I'll try it again. Send one, and then another one. Try to catch the first one on the way back. Alright.
Wait for it to hit the back, and then as soon as it gets to the end, hit it.
Okay, let's see.
So it's immediate.
I'll try that. Alright. The thing is, you should notice a couple of things. That when a wave that's going through like this, when it hits the end, it experiences a bit of an action-reaction thing. So the wave comes in and pulls up hard up against this, okay, which then it in turn pushes back down again. Action-reaction, right? And so the wave comes in above, but it comes back inverted. Alright? Because it's pushed it back down. As though when my hand goes up, this one acts like it went down. Alright? And so it comes back under rather than over. Alright? Which means that when I send another one that's over, when they hit each other on the way back, if I can do it right, they should kind of like flatten out for a bit, right in the middle as they cross each other. So I'll try again. It's so hard to see because it's so quick.
So when they collide, does it change the peak?
Yes. It's the amplitudes that become the sum of the amplitudes. So if they're both up,
They stay like that.
they add up, right?
Yeah.
If they're opposite, then they cancel out.
And then they keep going. Like
And then
that.
they keep going past each other. Yeah. But because there's a lot of energy wasted in this, it kind of dies out. This diagram, that's what they're trying to show. Two waves go through, they interact with each other, but their y components add, so you end up with superposition, but the energy's still there and it's still moving in opposite directions. And so as they cross, they go back to what they were. So that's this wave over here after the interaction. But if everything's nice and perfect, then you don't lose any of your peak. They just keep on going. They interact and then they pass. Ships in the night. Very romantic. So, now there's another Druitt Hewitt, the Doppler effect. Okay, the Doppler effect. Yes, the Doppler effect is part of the course. What the Doppler effect is if an object that is creating waves is moving, okay, then basically it scrunches up the waves to one side, spreads them out on the other side, okay? Does it change their speed? No, because you're still in the same medium, right? But because you're moving, as you're, for example, let's say you're moving along a long pool, like a lap pool, and if you're standing still and you're just got a ball on a bar and just hitting the water, you just have ringlets that go out. But if you're moving, relative to the medium, then the ringlets, you have to take that into account. The ringlets get closer to each other because you're moving up, because you're traveling with the last ringlet that you made. So it's coming with you, and you're kind of catching up to it. And so those ringlets crush up, and the ones at the back, well, they spread out because they're moving the other way, and you're moving that way, so they spread out. So you get the difference between this diagram and this diagram, all right, as you're moving. Now, the only thing to really consider here is that what difference does that make to what's happening? Now, we know how they know that the universe is expanding?
Yes.
It's the Doppler effect, right? Yeah, the redshift. That's right. So if everything's moving away from you, then the light behind it's spread out. So that pushes it towards the red part of the light spectrum. Whereas if everything was coming right at you, it'd be crushing up and you'd be pushing everything towards the blue side of the spectrum, right? That would be scary, yes. But getting away sounds better. It's just a cold spread out, thinly freezing universe that just... Right. Yeah, so now that's how they know that in the Doppler effect, using the Doppler effect, they figured out, there's a redshift on everything, which means everything is moving away from everything else, right? So that's how they knew that. The other example is that when the fire truck or the train, they always use trains. Scientists love trains because trains are awesome. So the train blows its whistle as it's approaching you, and it seems to go up in pitch. Now, it goes up in loudness, obviously, but not because of the Doppler effect, because it's just closer to you, okay? So it's just closer to you, so it's louder, right? But it's not a Doppler effect thing. The loudness is not the Doppler effect. The Doppler effect is about something else. As you scrunch up the waves, it gets really, really, really high pitched, and then it goes past and goes really low. Then again, where the confusion comes in is students go, it gets louder and then gets quieter. Yes, but that's just about how far away you are from the whistle, okay? But it's the pitch that is the Doppler effect, okay? Remember, high-pitched sounds have very, very high frequencies. Low-pitched have very low frequencies. That's what the difference is there, okay? So the Doppler effect is about the pitch. It's not really about the loudness.
So it's like a race car going past you out.
Yeah. So yes, it's louder as it's there, but it's really about the high sound that you're hearing. That's what you're attributing to the Doppler effect. We just want to go to polarization right now. Your cool, sick, polarized lenses, do we know how they work?
Yes.
They stop reflection.
Go. How do they cut down on glare, but why and how? Experiment that says light is a transverse wave. It has to be, otherwise polarization wouldn't work. Imagine if light was a compression wave, like sound. How could you line up your grid, like your lines, to block out light that just blocked out that only allowed one plane of light through? You couldn't. So what I'm talking about is this here shows you the transverse wave, right? Now imagine my Polaroid lenses are bars, basically, right next to each other that are this thick. So this is a wave that's traveling through space. Now it's a light wave, okay? And I've got my Polaroid lenses with the bars like this, that only let light in this plane through. Every other bit of light, every other orientation gets blocked, can't get through. But only light in this orientation gets through, okay? So all the glare, all of the light that is in every other orientation, as it's coming at you this way and this way and that way and that way and that way and that way, they all get blocked, except for the one that lines up with the lines of your Polaroid lens, okay? Just like that. And they slip through, and that's enough light so you can see everything nice and clear, right? So check out these. This is going to blow your mind. Right, watch. I've got two Polaroid lenses right here, and you can see through them. See, you can see me.
Not really.
Oh, you can. I'm just because you don't get the glare from my radiance.
Yeah.
Okay, so you don't get the glare. Oh, yeah, up against the thing. You can see through it, right? Now they are lined up with each other so that the lines are like that. Okay.
Oh.
Now, but there's two of them, right? There's two of them, one in front of the other. What happens when I make them perpendicular? You won't be able to see anything.
Is that what smoke glass is?
Wait. I don't know. Wait. Bam. And it goes opaque.
That's like.
You can't see anything
That's
through it.
like
Okay? Because now the light, the gaps in the Polaroids are this way and this way, meaning every orientation of light is out.
The only thing that's
Okay.
making that not look like your black is the fact that the plastic is has glare on it.
Yeah, that's right. So do it again like that, and if I turn it, and all of a sudden it becomes, you can see through it again. All right? So that's crazy, right? How cool is that?
Both ways, can you not see?
Yeah, it's both ways, That way or that way, doesn't matter.
Yeah,
But if you crisscross them, bam, doesn't matter.
Okay, so it's not like one way.
No, it's not. Yeah.
Ooh.
Ooh, it could be. I haven't looked at what tint actually is, but it might be because tint allows you to get very clear vision without, but still losing a lot of the light.
Put it up against the projector because we can see it glaring onto the actual thing. It's a projector that's projecting onto the glass.
All right. So what I'll do is over here. So you can.
Yeah. So it's like, hold on, I'm seeing.
So you can see that, and then as we turn,
That's cool.
you get nothing, right? And that's how Polaroids work. Now, interestingly, if you watch any old movies when they just invented like 3D animation, not 3D animation, 3D film, as in three-dimensional movies like short 3D glasses, right? Remember in the old days, one was blue. One lens was blue and one was red. That's the old days version.
Is there a new version?
Well, the new version is when you go and get those 3D glasses now, they just look like tinted.
Yeah.
They don't have color. And like I was talking to my little brother and he was like, yeah, because they've polarized them. Because polarizing is so cheap, they've just gone, action. All right, the only real maths that you're doing here is the wave equation, V equals F lambda. All right, now we do need to be a little bit careful because there's some other little bits and pieces that actually might be part of the next chapter actually. Okay, we've got here F equals 1 on T. Now on the last sack, everybody understood that. That was really good.
Yeah.
And that was really good that everyone knew that what 1 over T was and the relationship there. Now there is also
Last second, as in what?
as the one we just did. Yeah. I think there was, yeah? Was that the last sack or was it the one before? All right. Now, look, that means that you can also write V equals lambda on T if you sub for the F, okay?
Oh, is that frequency?
Yes, frequency. Don't forget, frequency is measured in hertz, okay? So, how many cycles per second you're getting? Okay, so there's your frequency. And 1 over T, or so therefore T or period. What am I doing? Okay, so period, which is T, is equal to 1 over F. So please, that's really useful, especially for this wave stuff, okay? And there's something else that's to do with lambda that I can't remember right now, but we'll get to that later. Anyway, so if we have a real quick look at... Yeah, I hope so. I'm going to edit it out if I can't. Okay. Wait, it's question 1. One's really easy. When a wave moves through a medium, there is a net transfer of energy only, obviously. Along a transverse wave, there is a net transfer of Energy. Yes. Energy. Be energy only. That's right, yeah. Number 3. If in a longitudinal wave, the direction of energy flow is, okay, longitudinal. Don't forget, that's this wave here. There is, you know that the particles are moving in the same direction, roughly, so half of the time in the same, half the time opposite, but they are in parallel. The particles move parallel to the direction of the motion of energy, okay? So then you've got to find yourself an option that's closest to that. So, is perpendicular? No, not perpendicular. Is in the same direction as any temporary displacement of mass. Depends on the maximum temporary no. Depends on the phase of, no. It's B is the closest thing to a good answer then. No. It moves, but it never ends up moving away from where it was. So you know what I mean? Yeah. It has, yeah. That's a very nice way of saying it. It has a displacement of 0 once the energy is gone, but it has a distance traveled. Yeah, but the energy is the one that moves it, but it leaves it where it was when it's finished. So it would be, is in the same direction as any temporary displacement of mass. In other words, the energy, see, it's like that, yeah, that. So it's in the same direction as the flow of energy. Here, the flow of energy is perpendicular.
So that's like a surely. Oh, so it's not when sound hits like.
Yeah. Sorry?
Surely we get a DC motor and put it on there really slow.
We're going to do a what?
A DC motor and put it on it really slow, which is always moving.
So we always can see it, remind us.
So cool.
Yeah.
To have that just always moving. Add like a lava lamp element to it.
Lava lamps are oddly amazing and great. Yeah. Oh, okay. All right, watch. One thing that I did neglect, one thing that I missed, is a point on the wave. That point P, okay? That point P. Is it, if the wave is moving in this direction, now I'm not really answering this question, I'm just giving you another thing that I've realized is part of a lot of questions that they ask, okay? So, if the wave is moving in that direction, is P about to move up or is it about to move down?
It's about to move up.
Okay, good. It is about to move up. Okay, now, if P is just a point like on the string, it's a point on a string that I've coloured in, right? So it's not going to move. It's not going to go left or right. It's going to go up or down as the wave moves past it. Is P about to move up or is it about to move down? If the wave is moving to the right, yes. Yes. So think about it this way. If you're at the beach and the wave is coming from behind you, it pushes you up. It doesn't push you down. It lifts you as the wave goes past. Point P is just a spot like on a string. So, yeah, that's right. Now, the way you can always get it right is that the front of the wave or the back of the wave? Now, it matters whether you're talking about, are you talking about the wave going this way or that way? So going this way, that's the front of the wave. And you always go up on the front of the wave. It's the back of the wave that you come down on. Okay, yes. So as you move, if we've got point Q here, is Q about to move up or down? It's moving down. It's on the back of the wave. That's the other little thing that they chuck in there for some of these questions. Just identify the front of the wave or the back of the wave, and bam, you know what's going on. All right? Beautiful.